As physicists, we've enthusiastically guessed this for over a century, beginning in the year 1916. This occasion marks a momentous accomplishment, imparting a short inspection of one of the universe's most charming and cryptic peculiarities: black holes. These grandiose monsters, acknowledged for their massive influence, continue to be relatively elusive. While they're epic in terms of their gravitational effect, they are nearly undetectable, making them even more perplexing. One such black hole, probably weighing between 2 to 4 million times the mass of our Sun, may be the subject of this discovery. Over the last several decades, research devoted to black holes has transformed our knowledge, taking us from a place of absolute ignorance to one in which we're beginning to get a close observation of them. Now matters have taken an even more interesting turn, as physicist Michio Kaku has revealed that we have finally figured out a way to look inside a black hole. This discovery opens the door to a wealth of new facts that could illuminate aspects of science we may have ignored in the past. Let's take a deep dive into the world of black holes and find what exists within them. While space is limitless and vast, the concept of black holes raises infinite inquiries. The history of black hole. Research, before we start discussing the specifics of Kaku's splendid findings, it's important to apprehend the primary nature of black holes. While there's sizable recognition of what black holes are, sizable gaps in our understanding continue to remain. The idea of black holes dates back to 1916, when Albert Einstein published his general theory of relativity. This theory predicted the existence of black holes despite the fact that, at the time, the idea was solely theoretical. It wasn't until about 50 years later in the 1960s that substantial evidence for their existence started to surface. Researchers studying the constellation Cygnus discovered an unusually bright blue star emitting X-rays. They found that this star was not stationary, but instead orbiting a massive dark object. Upon further examination, it became clear that these X-rays were being integrated into the object, leading to the coining of the term black hole. This discovery was a historical turning point, proving that black holes were not just a product of Einstein's imagination. They were real, tangible entities that existed in space. It became clear that we needed to study them in greater detail. Scientists from around the world began focusing their research on a specific black hole in the Cygnus constellation, designated Cygnus X1, which lies approximately 6,000 light-years from Earth. This black hole was millions of times brighter than the Sun and exhibited extreme density, with a gravitational pull so intense that not even light could escape it. This was the primary characteristic of a black hole, the potential to trap light within its gravitational embrace. Understanding the nature of black holes. The nature of a black hole is both fascinating and terrifying. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape it. Any object that ventures too close to a black hole is sucked in, and once it passes a critical boundary, it is lost forever. This inherent danger is why it is essential to expand our knowledge of black holes. After the discovery of Cygnus X1, researchers launched an extensive search for other black holes. Current estimates suggest that there may be over 100 million black holes scattered throughout the Milky Way galaxy. However, because of their nature, these cosmic giants are quite difficult to detect, meaning we do not have an exact count. One of the major issues surrounding black holes revolves around their gravity. Their gravitational force is so massive that anything getting too close is gradually compressed to an extreme degree until it becomes a dark singularity. To put it simply, black holes function as cosmic vacuum cleaners, pulling everything in with an insatiable force. One of the most unsettling aspects of black hole research is that if someone were to fall into one, they would be stretched into a long, thin shape due to the tidal forces acting upon them. This stretching would occur gradually, and the person would perish before reaching the final stage of this process. To be clear, it is best to avoid falling into one at all costs. Although the closest black hole is about 500 light-years away, it still raises questions about the possible threats they pose to us. The first photo of a black hole in 2021, a remarkable achievement was accomplished when scientists successfully captured the first clear image of a black hole. This specific black hole was located within the galaxy M87. The research team took several photographs over multiple nights, and by stitching these images together, they created a comprehensive picture that revealed stunning details. It appears that a black hole is not merely a massive void of nothingness, as many people assume. In fact, a black hole consists of three distinct layers: the event horizon. Once an object crosses this boundary, there is no turning back. It will inevitably be pulled into the black hole. The photon sphere, a region where light itself can be trapped in orbit around the black hole. Any light entering this region becomes trapped by the black hole's gravitational force, unable to escape. The singularity, the point at which everything that falls into the black hole is crushed down to an infinitely small point. This is where the laws of physics, as we understand them, completely break down, making it impossible to predict what happens next. Theoretical possibilities. Wormholes and time. Travel. What is even more fascinating and alarming is that no black holes are exactly alike. While they all follow this three-layer structure, their behavior can vary significantly. One theory suggests that black holes may be connected to wormholes, hypothetical passageways that link two separate regions of space-time. Some theories even propose that they might connect parallel universes. If someone were to fall into a black hole, instead of being crushed, they might travel through this wormhole and emerge in a different universe, or even at a different point in time. According to Einstein's theory of relativity, space and time are intertwined, forming a four-dimensional fabric. Objects with mass distort this fabric, creating a gravitational field that causes other objects to move toward them. Imagine space-time as a sheet of paper. If you place 2 points on it and draw a boundary between them, that represents the path objects take through space-time. However, if you could fold the paper, you would create a shortcut between the 2 points, similar to a wormhole connecting two distant regions of space-time. The future of black hole. Research wormholes are not just science fiction. They are a direct prediction of general relativity, but no one has discovered one yet. Intrinsically unstable, wormholes can implode very quickly. The potential for wormholes to act as pathways through space has intrigued physicists for a long time. While the idea of traveling vast distances in a moment or even venturing through time is certainly exciting, Einstein's special theory of relativity predicts that nothing can travel faster than the speed of light, which places an absolute limit on wormhole plausibility, at least with our current understanding of physics. Physicist Michio Kaku has been working on a unified theory that might help explain black holes. One of the greatest challenges in modern physics is reconciling general relativity with quantum mechanics, two powerful yet seemingly incompatible frameworks that describe the universe at vastly different scales. While Einstein's theory of general relativity explains gravity and large-scale cosmic structures, quantum mechanics governs the behavior of subatomic particles. Black holes exist at the intersection of these two realms. They are massive cosmic objects, but they also contain singularities, infinitely small points where space and time break down. To truly understand black holes, scientists must develop a unified theory that merges these two pillars of physics. Physicist Stephen Hawking made significant contributions to this pursuit with his theory of Hawking radiation. In 1974, he proposed that black holes are not entirely black, but instead emit tiny amounts of radiation due to quantum effects near the event horizon. Over time, this radiation causes the black hole to lose mass and eventually evaporate, a process that challenges the long-held belief that black holes are permanent. Hawking radiation introduces a paradox. If a black hole ultimately evaporates, what happens to the information about everything that fell into it? This information paradox remains one of the greatest unsolved mysteries in physics. According to quantum mechanics, information cannot be destroyed, but if a black hole vanishes, it seemingly takes all its information with it. Can black holes be gateways to other universes? Theoretical physicists have long speculated that black holes could serve as gateways to other parts of the universe, or even to entirely different universes. This idea is based on the concept of Einstein-Rosen bridges, commonly referred to as wormholes. If wormholes exist, they might offer shortcuts through space-time, allowing for faster-than-light travel. However, they remain purely theoretical, and their stability is uncertain. Many physicists believe that exotic matter with negative energy would be required to keep a wormhole open long enough for anything to pass through it. One intriguing theory is that what we perceive as a black hole could actually be a white hole in another universe. Unlike black holes, which trap everything that enters, white holes are hypothetical objects that expel everything, making them the opposite of black holes. Some theories suggest the concept has yet to be experimentally confirmed, and a lot of its predictions remain untested. Theoretical physicists like Michio Kaku are working tirelessly to unify these two main pillars of physics, quantum mechanics and general relativity, into a single unified idea that may explain the entire spectrum of phenomena. A concept of everything, at all scales, would not only provide a deeper understanding of black holes and other special objects in the universe, but could also shed light on the very nature of space-time itself. The idea of extra dimensions, as predicted by string theory, may help explain the hidden forces that govern the universe. It suggests that what we perceive as 4 dimensions may actually be a small slice of a much larger and more complex structure. Another area of intense study is the role black holes play in the evolution of galaxies and the structure of the universe. The discovery that extremely large black holes can be found at the centers of most galaxies, including our own Milky Way, raises further questions about their influence on star formation rates and galaxy evolution, even the ultimate fate of the universe itself. The concept that black holes could play such an essential role in shaping the universe adds another layer of complexity to their already mysterious nature. Furthermore, the intense radiation emitted by black holes called Hawking radiation, named after the renowned physicist Stephen Hawking, has led to fascinating discussions about the ultimate fate of information inside a black hole. Scientists have debated whether information is lost forever when it crosses the event horizon of a black hole, a concept known as the information paradox. Hawking's groundbreaking work suggested that black holes could emit radiation that gradually causes them to evaporate over time, potentially resolving the paradox. However, this remains an active area of research with no definitive answers yet. What is clear is that the study of black holes has provided profound insights into the nature of gravity, space-time, and the universe as a whole. It has also opened the door to a new frontier in physics. Black holes challenge our comprehension of the laws of nature and continue to provide a foundation for novel theories and discoveries. As our observational tools improve and we explore deeper into the quantum and relativistic realms, we are likely to uncover even more profound truths about these enigmatic cosmic objects. The journey of scientific exploration, like the mysteries of the universe itself, is bound to take us to places we never imagined. As we push the boundaries of our knowledge, new questions arise. If black holes can act as cosmic engines shaping galaxies, could they also affect the fundamental nature of time itself? Some physicists suggest that black holes might store information about the past, effectively preserving a record of the history of the universe within their event horizons. This idea connects to the ongoing debate about the information paradox. If information is not lost, where does it go in a black hole? One hypothesis suggests that the information might be encoded on the event horizon itself, an idea known as the holographic principle. This theory, developed by physicists like Gerard 't Hooft and Leonard Susskind, proposes that all the information contained in a three-dimensional region of space could be stored on a two-dimensional surface. If true, it would mean that our entire universe might function like a giant hologram, with our perception of reality being a representation of the underlying quantum information. Moreover, if wormholes can exist as stable structures, they might be more than just cosmic shortcuts. They could also serve as information channels. Some researchers speculate that quantum entanglement, a phenomenon where two particles remain connected across vast distances, might be linked to microscopic wormholes, forming what is sometimes referred to as the ER-EPR conjecture, named after Einstein-Rosen bridges and the Einstein-Podolsky-Rosen paradox. If this conjecture holds, it could suggest a deep connection between space-time geometry and quantum mechanics, potentially leading to breakthroughs in understanding gravity at the smallest scales. The future of black hole research is promising. With advancements in observational technology, such as next-generation space telescopes and gravitational wave detectors, scientists hope to gain even more insights into black holes. The James Webb Space Telescope, JWST, has already begun providing unprecedented views of the early universe, while the Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect low-frequency gravitational waves produced when black holes merge. These tools will help answer some of the most pressing questions in astrophysics, such as how black holes evolve over time and whether they truly act as bridges between different regions of space-time. Meanwhile, laboratory experiments in quantum mechanics are shedding light on the mysteries of gravity. Some physicists are exploring the possibility of creating artificial black hole analogs using Bose-Einstein condensates, ultra-cold atoms that mimic certain aspects of event horizons. These experimental setups could help test some predictions of quantum gravity in a controlled environment.